Hello, everyone. This is a show and tell, something that we built in the last few months, and the background to this is something that's hidden in plain sight, and that's the electric power network. So unless it actually catches fire or explodes, you don't generally notice it, or maybe it's blocking your view, but I think it's in the news lately. So this came off Transgrid's website. This is the New South Wales main transmission system. All of these are very high, 500 and 330,000 volt lines. You can see, I don't know, does the cursor work when I'm in presentation mode? Maybe not. But you can see that blue line around Sydney connecting a bunch of coal-fired thermal power stations. This purpose of this whole network is to move tens of thousands of megajoules per second between Snowy Mountains, Hunter Valley and Sydney and the regions. And we're going to dive into that inset because this is sort of like a fractal or a blood supply system. The more you zoom in, the more detail there is. And this is, we've projected a bit of Endeavour Energy's network onto Google Earth here. And these blue and purple lines represent the arteries of their system. You can see they go down the south coast and out west of Sydney. And as you go in now, I've just jumped up right up there in the top left is Katoomba. And seeing it's very scenic, I thought we'll go there. And as you get closer, you can see green lines running down the streets and blue circles that represent pole top transformers. And you can see some little red squares that represent automated switches. And we're interested in this one, which is can't quite see the one I'm interested in here, but 9313 is a sub. We're interested in 72985. And if we come closer to that, it looks like this. So can you see there's a radio antenna, VHF radio antenna there, and a box on the pole that's got a computer in it, and up the top is a electrically controlled switch. And from that radio antenna, this is what we get back. The switch we're concerned with is the one in blue. You can, if you look, this is the raw data and it's over a period of I think that's 2 days. And you can see that, well, it's pretty all over the place, but it is, you can notice it's been quantized somehow. There's too many straight lines in that to be per chance. And it's sort of quantized on time as well. So can I switch screens when I'm in here, or do I have to exit to do that? So if we look at raw data for we'll come here. Yeah, this is the same stuff over a longer period. So here's the thing, we're collecting this and we're stuffing it in a Cassandra database cluster. But it's not directly usable by the planners and the forecasters because the data is too voluminous. Once you take any decent stretch of time, there's just too many points for something like MATLAB, for example. And the other thing is it's all irregularly spaced. So most of the tools that our users want to use don't like irregularly spaced, irregular time series. So one of the things you could do is interpolate. Imagine these little black squares are the raw measurements, and we interpolate, and then we take the area under the interpolation. That's one form of resampling that has the property of preserving the timing and the overall energy under certain assumptions about how the points have been buggerized on their way here. You also have to take into account that we have periods where we may have lost telemetry, and you have to really detect that. You can't just run your interpolation over a blank spot and tell the forecaster that, you know, this is what happened. So, as I said, I won't show you the ingestion side of our system, but the data ends up in a Cassandra cluster. The piece of software I want to talk about is labelled Metrovor on this block diagram. And Metrovor is going to make sense of all this data and package it up in a way that MATLAB user could use, or could be used in a user interface, you know, web browser. And you can see that there's a reference to something called a tag list. And I'm going to talk about, that's really an obsolete name for a little query language we've developed. And we have a repository of tag lists. It says Oracle. That's no longer Oracle. We found that we could replace those two boxes with Elasticsearch without too much hassle. So the sorts of transformations and operations we want to be able to do on the raw data, I've mentioned the resampling, interpolation, and there are other forms of smoothing. There are also reductions where you take an entire span of data and reduce it to a single figure or set of figures. You might want to map a function over it, like a conversion from one set of units to another. They are also, in electric power, trig functions are used to convert data. The other thing is that we may want to bring a number of series onto the same time intervals. So we'll call that join on timestamp. I call it inner join. We may want to combine time series, sums, products, averages across time series, derive stats like histograms, peak value, by which I mean sort of the 97th quantile perhaps, or percentile. We may want to compute durations, how long on average is the signal above a certain level. The reason that this is our scope and not some other tool like MATLAB, SAS or whatever, is that we want to do the stuff that has to be done on the raw data, which is voluminous, and then we're happy to stop, and then we'll let the planners and forecasters take over and do modelling. So to bring all of these operations together, it's an opportunity to create a little language. And you can see by these examples that our little language is sort of encoded on top of JSON syntax. And in fact, we looked at earlier JSON artifacts that we had, and we found that they all had a common structure that's also embodied in this little language. And you'll see from the terminology here that the little language is really, it's just a kind of Lisp. So it has only three constructs. A call, which is just a JSON object that says what to call and some parameters. let, which defines a few symbols and then makes them available in an inner scope, and join, which combines time series together, effectively putting them in one big bucket. Say a little more about that. So, nothing like the simplicity. If you want simplicity, I think it's been said that your average scripting language is just Lisp with some other syntax imposed on it. So this is a great way to start, I think, but it can get tedious. So we do allow some abbreviations. For example, that top block of JSON can be written as in the center there by simply assuming that where a parameter is not supplied, then it's taken from the enclosing let block. First abbreviation. Next abbreviation is we call history constantly to take stuff out of Cassandra. So if a string is in the correct form, that's translated at an early stage in the language to a call. And so we can get down to something that people are kind of happy with. They're only mentioning the things that they care about. Time, in that example, times and the names of time series that are found in Cassandra. The other thing is that by approaching the little language this way, you get this ability to compose fragments. So, is there anyone in favour of composition here? So in this example, which I actually use, the first fragment is just asking for raw data within certain limits and is attaching some labels to it. The next fragment is asking to translate, to do a resampling called series average over some raw data to be supplied. And you can combine those two little programs into one just by textually putting them together as I show on the bottom there. And that's done all the time in the web browser, and it allows you to treat little fragments of this language almost as if they're predefined functions. Now the results that come out, remember that there's a join operation. There's a join operation, one of the three. If you take a number of time series and you just put them in square brackets, they're joined and they'll be organised like this on the left. If you, each one of those little blue and yellow boxes is meant to represent a series of samples forming a time series. Now, at that point, that might be the final output. It can be presented just as it appears there, one, then the other, or it can be decimated and all of the individual little yellow squares, which are called events, could be all mixed up, but with tags on them. But that's not always what you want. Sometimes you want a thing like a frame, which is a tabular structure, where every row applies to a specific time. So an inner join function does that. So this is basically, we have this sort of theoretical form for the output of one of our queries, and then we encode it in a number of different ways in JSON or CSV. Well, the language, we've just sort of at an early stage, but the language is proving popular so far. One of my colleagues at Endeavour built this application, which is a GUI for building expressions in this language. So rather than you having to open an editor and type it in, and it's coupled to the metadata that knows what the contents of the Cassandra database cluster are. So Metrovore, that piece that sits in front of Cassandra is written in Scala, and this is a block diagram. At one end there's Jetty, at the other end is the DataStax Cassandra driver. In the middle we have some Scala-ish wrappers around those two pieces. We have the guts that have to compile our little language into a plan, then execute the plan. And we have a few bespoke utility or abstractions. One of them is transducers borrowed out of Clojure. Another is a fairly generic task-like monad, similar to task in ScalaSyd, with a few differences. And we have, at the heart of keeping this efficient is a system of managing buffers. So the intention here is to perhaps just show a couple of items out of the Scala, because this is ScalaSyd. Jed, how am I going for time? How long have I been talking? Yeah. Okay. So I don't know whether I'm going to have to make this a bit bigger, aren't I? This is the first thing that you'd expect to see. It's a trait and a set of case classes that represent an expression in our little language. You can see the main parts of the language. There's let, call, and join up there. But notice that even though the language is recursive, this family of case classes is not recursive. It's got a type parameter A, so it's actually a functor in the jargon that we use. And that makes it far more flexible than if we just directly made, for example, join refer to a list of exp instances. Instead, join refers to a list of A's, and that allows us to do all sorts of tricks, including use canned recursion schemes. But even if you don't use canned recursion schemes, it does allow you more flexibility when you're even writing recursions manually with an ADT. And here you can see the map function can be generically written. I'll just put my glasses on. That language is eventually reduced to a tree of operations, and as development went along, we refined this list of operations, and eventually we got to something that's somewhat canonical. Some operate vertically along a time series, some horizontally across time series, some are just mapping over an array of time series or a frame, and so on. Very significant part of this that I won't mention further is attaching labels to time series so that when they emerge from Metrovore, the individual events can be grouped in whatever way the analysis or visualization wants. So the implementation ultimately boils down to not sure which end to start. It ultimately boils down to things like transforms, and these, I'll come back to that. These transforms are written in terms of an abstraction called a transducer, and its partner, a reducer. So a reducer is simply a fold, but it's different to the fold abstractions you might find elsewhere in that the reduction state is private to the reducer, and there's never a time when that's exposed outside the reducer, and that makes reducers more composable, and transducers are the mechanism for composing reducers. So a transducer is just a generic function that takes one reducer, changes its type, produces another reducer. You can see that in the first apply, and it's got the usual function composition operations on it. At the other end of a chain of reductions, we have to have, so the reducer is taking A's and reducing them to an S. At the other end of this, we have to have some way of educing A's out of some generator. So there's a property called educible, which can be associated with either asynchronous or synchronous sources. Now, with that abstraction available to us, it becomes a way to write time series analysis functions that we're interested in. So, for example, the average one that I showed a diagram of at the beginning is created here. We start with normalized windows over the irregular data. This little arrow means composing a transducer with another transducer. So it's just a symbolic way of saying and then. Group by the period of the desired resampling period, and then collect the samples into that group using an aggregation operation, and finally produce the output samples. So that's the transducer abstraction. These abstractions, you'll notice that transducer refers to something called a context. So it's possible to define these things so that they're producing asynchronous results, but we don't really want to do that. We want to use an unlifted version of these abstractions for speed, and we want to specialize it as much as possible for doubles. So we arrange the data into buffers, and this is not a very functional looking interface. Yes, it's immutable, but that's all you can say about it. Notice that the buffer type here has got no type parameter. And it's got a series of methods that you can query it with. So not really the way we write functional software, but it is the perfect way to encapsulate a series of arrays arranged in columns for maximum performance in terms of cache hits. So, the performance issue that we're fighting here is never the CPU, which can execute instructions enormously faster than you need to. The performance hit we're dealing with always is we can't load the cache in front of the CPU fast enough from main memory. So that's our buffer, and there's a few instances of this, such as empty buffer and a constant buffer and so on. But the main one is the array buffer that contains arrays of doubles in column arrangement. Now, having created something monomorphic like this, it's really desirable to bring that into a polymorphic context, even if you don't need it. So we have a concept called a stage, and it is what we do the rest of the implementation in terms of. And it is function-like. It's got an input and an output type, And even if those input and output types are still going to be buffers, it's a smart thing to make them type parameters, because it keeps all of the code for implementing stages clean. You can distinguish whether you've accidentally processed an output when you meant to process an input, or whatever, because the types don't match. So even if in the end a stage is really going to be dealing with buffers in, buffers out, it's better to define it this way. Now once we get at the buffer level, we can now start dealing with asynchrony. And what we do is we lift these transforms that you saw before into the buffer type, such that they become transforms of buffers. And we put the whole lot inside processes. And a process here is just, as I said before, it's similar to a task. The main difference is in the error recovery for this. It has a state called failed, and that means, and there's no implementation in the process type. Instead, the implementation is deferred to another type called site, and that allows us to treat failure a bit the way actor systems treat failure. If any part of a complicated process signals fail, the site is notified and can shut the entire request and response down without. The alternative is passing failure through and having it as one of the alternatives of in the output of the process. So that's a little bit of a tour of the, without going into a whole lot of detail, of the abstractions underlying this software. And that's all I've got.
Awesome. Thanks, Arnold. Quick question. Process, is that the stream abstraction, ScalaSyd streams, or something similar?
I effectively use them as if they're streams, but it's much closer to the concept of task than stream.
Right. Yeah. But it's your own hand-rolled...
My hand-rolled task, yeah.
Got it. Yeah. Fair enough.
In order to make streams out of them, there's a couple of approaches. One is you can lift a process into a co-free. Since you're familiar with all those sorts of things, I can say that to you without... and that effectively makes a recursive computation that for every step a process must run, and or a process must be bound to another process, or flat mapped to another process, and that creates then a series of values. So that's one way of turning a process into a stream. Yeah.
Interesting. All right, Andre.
So I noticed that you've got the algebra that is that your operations are defined as a algebra there.
You're referring to what? This
the
thing
expression
here?
algebra, yes.
Yep.
And then by the time you'd finished with it, you said you've managed to get the Scala compiler to see completely monomorphic code, so that you don't have the virtual calls and you get the efficiency.
It's a long way down, yes.
How did you actually force that into monomorphic, force the compiler to accept that as monomorphic?
Right. So this tree that you see here closely parallels the JSON structures that you saw earlier. So that goes through a translation stage. We're still dealing with a tree-like structure, and then we do two interpretations on the tree. One interpretation, we generate all of the labels that are going to be attached, because the labels can be done ahead of time before we've actually accessed Cassandra. And the other evaluation of the tree that we do is to turn each of these operations into a stage, which is defined in terms of streams. And it's at that point that we lose the types, because we're now, these A's that you see here all become buffer. And then at lower levels than buffer, where we're dealing with transducers and these transforms and so on, these are all operating on doubles. So we've now crossed over and we're out of the polymorphic zone. I don't know if that's exactly answering your question, but yeah.
Can I just clarify that? When you say you're out of the polymorphic zone, do you mean that although your source code is heavily polymorphic, there's only a handful of types being run on the actual JVM, and the JVM will learn that it can specialize it? Or do you mean something else?
I do mean that, but I think the chief efficiency is in that we're able to use actual arrays of doubles rather than array of T, and that eliminates a whole lot of scatter gather. At least the theory is. I had hoped to have some simple little performance comparisons developed to justify my contentions here, but I'm sorry I don't have that for you tonight. But yeah. We don't bother with by specialization. You mean that the various methods have been special cased for a basic type such as double. So we do that at the very last resort, at the lowest level.
It's quite an interesting kind of, and it's quite involved topic, like how to do specialization at the JVM level with Hotspot. This one is simply because you're using arrays of doubles. So you have the specialization simply on that data type, as opposed to specialization, a monomorphism kind of restriction, which would also potentially help in terms of what the Hotspot could potentially do for it. But in this case, because you're using arrays of doubles, the data type is your, the specialization. So
we suffered the pain. We wrote the code that the compiler might have written, if you like. Yeah.
Yeah. So that is specializing in this case.
Yeah.
So it's kind of handy. Any more questions?
Code anywhere.
Is the code anywhere?
Right. Gee, it'd be great if someone was interested in this. These ones in pink, I think I'd like to put up on GitHub. I've got old. If you go to my GitHub account now, there's all kinds of rubbish there and old versions. So I've been meaning to put up some clean versions in the hope that someone's interested in it. It's pretty much expecting people to, I think, depend on a library that so few libraries succeed. I think it's got potential as learning or teaching material perhaps more than as a library that you'd really use. I mean, no reason not to use it except that there's so much competition. The green ones too, I can put up. So everything except for the except for those ready ones in the middle. Yeah.
So for a project at this scale, how do you approach the planning? Like, do you plan from the top down, or you just write as you go?
Well, I did my best, but it didn't go well from a planning point of view. That process that we've been talking about, where we compile a plan down, we compile the language down to a plan, then we translate the plan into stages, pipeline stages, was really difficult, I found, to get my head around. And so it actually took me a lot longer than I foolishly claimed. But that's absolutely the first time that's ever happened with software. I don't think
It is actually an interesting question, simply because there is a certain amount of computer science involved in the basics of, creating a expression language based around some kind of fairly well-established thing. So if you don't have that, then it's going to take you a lot longer, because these are some basic computer science principles of Lisp and so on, that having those things are a huge leg up. So
absolutely,
you have to kind of invent those things for yourself from first principles. It may take you a hell of a long time.
You can get into analysis paralysis designing even the smallest languages unless you realise that someone's already done it in the 60s.
So, yeah, exactly. We can rag on about JavaScript as much as we like, but Brendan Ike did know Lisp. Right? And he did have some vague idea of what he was doing so that he could build JavaScript in 5 days. Right? You can have opinions about the result, but nevertheless, he couldn't have done as much as he did without a fundamental basis in, or a basis in the fundamentals. That's really important.
Yeah, I feel that very strongly. You put it well. You definitely don't want to be wandering around going through all this massive design space that's already been explored. You move on.
Yeah. Cool. Last question. All right. Cool.
All right.
Thank you very much, Arnold. Thank you.